Right, so you see a straight line over there, AB, and the second postulate says that I can continue that straight line further along in the same direction. And third, you can draw a circle with any given center and radius. So the center is a point. The radius is a line, finite straight line. All right, so you can draw straight lines, you can extend straight lines, you can draw circles. So let's just quickly illustrate over here. I have points A and B. I can connect them by a straight line. If I have a finite line segment already connecting 2 points, I can continue that line either to the left, passing through A, or to the right. I can extend it as long as I like. Usually it's depending on the other constructions involved on the page or on the board, exactly how long you continue to. And we'll see how that works in a moment. And down here, I'm supposed to draw a circle with this radius. I think I will fail. Okay, that's actually not too bad. Okay, so you get the idea. Those are the 3 postulates. The first 3 postulates. There are 2 more, as I mentioned. Okay, so let's see what we can do with these postulates. I'm going to take postulate 1 and suppose given 2 points, A and B, and then I connect them by a straight line. Good. And somebody else gives me a point C, and I can connect those by a straight line. Now, I have a question for you. Which of these 2 straight lines is longer? Well, that's easy. Obviously, it's AB, right? So AB is longer than AC. We didn't have to think about that one. But let's try something a little less straightforward. Here's A, here's B, here's C. Now, which one is longer? Well, if you come up close to the board and get a good look at it, you'll probably still be able to figure out which one is longer, but you get the idea. I can draw these close enough so that it's no longer something you can just eyeball. It will be actually a problem you need to work out. So here's my first question. If you had these 2 lines on a real board in front of you, what kind of physical tool might you use, or say on a piece of paper? If you had these 2 lines on a piece of paper, what kind of physical tool would you be able to find using which you would be able to settle this question of which of these 2 finite line segments is longer? All right, so I'm going to pause and let you think about it, and then you can type your answers into the chat, and then we'll resume. Right, you'd use a ruler. A ruler is a tool, maybe looks a bit like this. It has a straight edge marked at regular intervals, and usually those marks are separated by a distance of 1 centimeter or 1 millimeter, and numbers are put on the ruler to indicate the distance from one end. Okay, so here's the exercise I want you to do with me. I'd like you to imagine that you run into somebody who has never seen a ruler, has no idea how to use it, and I want you to explain to them how to take that tool and use it to solve our problem, that is, to see which of these two lines is longer. So think about it for a minute, and when you have an answer, a step-by-step series of instructions of how to do that, type it into the chat, and then we'll proceed from there. So one approach we can take to comparing the two lines is to rotate the ruler. So we start by placing the ruler along one of the lines. We then make a mark on the ruler corresponding to the point B. We then rotate the ruler until it lines up with AC. And then we look to see where the mark is. In this case, let's suppose it's out here. If that mark is further away from A than C, then we know AB is longer. If the mark is in here somewhere, then we know that AB is shorter. Right, so that's a pretty reasonable way of comparing the lengths of two finite line segments. What I want to do next is to take this story, which was about a physical tool, a ruler, and lines in the physical world, and manipulations of physical objects, namely rotating a ruler and comparing marks. Those are all things that we know how to do using our hands and our eyes and also our mind, but they're not mathematics. Mathematics proceeds from strict rules, like these rules. And these operations, rotating the ruler, writing marks on the ruler, comparing marks, none of that appears on my list of postulates. So in the next step, we're going to try and turn this operation we've learned how to do into something formal. It's time to return to the postulates. Postulate 1, you can draw a straight line connecting any 2 points. Postulate 2, you can continue a finite straight line in a straight line. Postulate 3, you can draw a circle with a given center and a given radius. So let's go back to our situation with 2 lines. I'll start with the first case, which is where AB is in fact longer than AC. We use the postulate 3 to draw a circle. So using postulate 3, I'll just write P3, draw a circle. If it does not meet AC, then AC is shorter. Okay, I hope that's pretty clear from the picture. Have a think about how that corresponds to the use of the physical ruler. The second case. We draw A, we draw B, but in fact AC is longer. There's C. When we go to draw our circle, so if the circle does meet, AC, then AC is at least as long. It could be exactly as long. As AB. Okay, so you can see how we replace the use of a physical ruler by this ability to draw circles and to recognize whether two figures intersect. This is one of our assumed powers that's not listed on the first board. If we draw lines and circles and so on according to our postulates, we are assumed to have the ability to see whether or not they meet. Okay, so if they do not meet, AC is shorter. If they do meet, then AC is at least as long as AB. This is still a little imprecise, but this is 90% of the way there. So let me move on to the final board and try and make this even more precise. Okay, so what I want to do is go back to this picture, and the thing that's a little imprecise about that is, well, it's certainly the case that either they meet or they do not meet. But why is it that not meeting, in fact, corresponds to our intuitive notion of shorter? That's sort of in the picture and you buy it, but we can be a little bit more precise about what Euclid means by shorter or longer or greater or lesser. That's what I want to do now. So I need a picture where AC is shorter. So here's our circle. Using postulate 2, extend AC. I'll draw this with a dashed line. And I'll call the point of intersection D. I'm going to leave aside for a moment the question of whether or not, in fact, such an intersection exists. Since A is the center of the circle, it just comes back down basically to the definition of a circle that such things exist. Not necessarily as arranged in this picture. This is only true if AC is in fact shorter than AB. Call the point of intersection D. Okay, now I don't want to say any more about that situation just yet. Let me draw the other figure. So this is what you would expect to see if AC was in fact longer. We draw our circle, and there's D. Okay, but of course not knowing whether or not C is inside or outside the circle, I can still apply postulate 2. Okay, so now, starting in a state of ignorance, where I don't actually know exactly what the picture is, and I don't assume that my magic eyes can tell the difference between the lengths, which we would call begging the question, if you assume the thing that you want to show. So without knowing which in fact is longer, I can do the following operations. I take my two lines, I draw this circle using the third postulate, I extend AC off in this direction using the second postulate, and then I look at this line. If the points are arranged in the order A, C, D, well, that means that the line AC is part of the line AD. So in that situation, AC is part of AD in the literal sense. And this is what Euclid means by lesser. Things that are part of other things, whether it's lengths or areas, are by definition lesser. So AC is less or shorter, I suppose we would say. Let's say less than AD. But AD is a radius. So equal. So equals AB. Okay, so that's if the points are ordered ACD. If we see instead the ordering ADC, and those are the only two ways of ordering points that start with A, and then have one of the two possible orders on C and D. If we see ADC, then again, AD is a part of AC. So AD, which is equal to AB, they're both radii, equal in length, I mean. So AB, which is equal in length to AD, is part of AC. Well, AB is not part of AC. AB is equal to AD, therefore less than AC. Okay, so you can see here how using postulates 2 and 3, I've arrived at one of two possible situations, that I can compare AB and AC by transferring the comparison, rather than being about two lines that are somehow going in different directions, to comparing two lines that are going in the same direction. So I've reduced the question to a problem about lines that are directly comparable, because one is a part of the other. And that is how Euclid thinks about comparing the lengths of two lines, without using rulers, just using the postulates. So I invite you to have a look at these boards and think about how we have taken this idea of comparing lengths from something that made use of physical objects like rulers and lines and marks, and turned it into something which was quite abstract, making use of only these basic postulates. That's all for now. Feel free to stick around. As I said, look at the boards, and I will be here, and you can ask me questions about anything we've talked about so far. Thanks for listening.